Have you ever looked up at the night sky and wondered, are we alone in the universe? The stars we see are just a tiny fraction of the billions in our galaxy, and each of those stars could host its own system of planets. With such staggering numbers, it seems almost impossible that Earth is the only place where life exists. Scientists have been asking this question for decades, and one of the tools they use to explore it is called the Drake equation. Today, we're going to dive into this fascinating idea and what it might tell us about the existence of extraterrestrial life. The universe is vast, over 100 billion stars in the Milky Way alone, and countless galaxies beyond that. But not every star has planets capable of supporting life. The Drake equation helps scientists break down the probability of intelligent life in our galaxy into key factors. The Drake equation was formulated in 1961 by Dr. Frank Drake, an American astronomer. He didn't create it to give a final answer, but to provide a scientific way to think about a question that otherwise seems almost philosophical. It helps us consider all the conditions that must align for intelligent life to exist and possibly communicate with us somewhere in the Milky Way. Here's a simplified way to think about it. First, we consider the rate of star formation in our galaxy. On average, about 1 to 2 new stars are born each year. But not all stars are equal. Some burn out in just a few million years, while others, like our Sun, shine steadily for billions. Life needs time to develop, so the type of star matters. Next, we look at the fraction of stars that have planets. Thanks to telescopes like Kepler and TESS, we know planets are extremely common. In fact, scientists estimate there could be over 100 billion planets in our galaxy alone. Even our nearest star system, Proxima Centauri, has at least one confirmed planet. Then we ask how many of those planets could potentially support life. Not every planet is in the habitable zone, the distance from its star where liquid water could exist. Some exoplanets are extreme, like Kepler 22b, which is 2.4 times the size of Earth and sits in its star's habitable zone. Could oceans exist there? We don't know yet. After that, we consider the fraction of planets where life actually appears. Life on Earth started relatively quickly after the planet formed, which suggests life might arise elsewhere under the right conditions. Next, we think about the fraction of life that evolves into intelligent life. Not all life becomes intelligent. Dinosaurs dominated Earth for millions of years without ever developing technology. Humans, however, evolved intelligence capable of building civilizations and exploring space. Could intelligence be rare, or is it a natural outcome of evolution? Then there's the fraction of intelligent civilizations that develop technology capable of communication. A civilization might evolve intelligence but never invent radio waves or other detectable signals, or it might destroy itself before reaching that stage. Interestingly, humans have only been broadcasting radio signals for about 100 years, a blink of an eye on a cosmic timescale. Finally, we consider the length of time civilizations release detectable signals. The longer a civilization exists, the higher the chance we could detect it. Imagine a civilization that has survived for 1 million years. What kind of technology could they have by now? Even though many of these factors are uncertain, the Drake equation gives us a structured way to think about the likelihood of alien civilizations. It's not about finding one definitive number, but about identifying the conditions we need to study to improve our understanding. Some scientists are optimistic. Given the sheer scale of the universe, billions of stars, each with potentially multiple planets, the chances of intelligent life existing somewhere seem high. Others point to the Fermi paradox. If aliens are out there, why haven't we found any evidence yet? Where is everyone? The Drake equation also guides scientific research today. It underpins projects like SETI, the search for extraterrestrial intelligence, which scans the skies for signals from other civilizations. It also informs missions that search for biosignatures on exoplanets, like traces of oxygen or methane that could indicate life. For example, scientists are studying TRAPPIST-1, a system with 7 Earth-sized planets, 3 of which are in the habitable zone. Could one of them host life? Only time and research will tell. Beyond the numbers, the Drake equation sparks imagination. It makes us think about what intelligent alien civilizations could look like, how they might communicate, and whether humanity could ever meet them. Could there be civilizations far older than us, observing the universe with technologies we can't yet imagine? Or are we the first to reach this stage of cosmic awareness? Fun fact: some scientists suggest there could be thousands of civilizations in our galaxy alone, depending on the assumptions used. That's mind-blowing. Just imagine the possibilities of contact, or even just knowing we're not alone. So are we alone? The truth is, we don't know yet. But the Drake equation reminds us that the universe is enormous, full of possibilities, and that the search for alien life is one of the greatest scientific adventures of our time. It challenges us to explore, ask questions, and never stop wondering about our place in the cosmos.